I'm Giorgio Metta. I'm from the Italian Institute of Technology, a research institute based in Genoa, Italy, and I work on human robotics, and in particular I'm the coordinator of the ICAB project. Today I'm going to speak about the ICAB, Human Robotics Project developed the Italian Institute of Technology. So these are the two robots that are actually being used in the let's say, first experiments. These are the data sets that we wanted to use as comparison because they're available from the internet. Almost everybody is being using these data sets. And the two arms that are shown here, one is hydraulic, the other is electric. And they're simply 7 degrees of freedom arms, like the ICAB basically. Though for the ICAB then we didn't consider the wrist and the hand, which are 3 more degrees of freedom, so we only use 4, while here there are all 7, let's say, joints available. So this is the first result. So these two plots basically show results in simulations and results with the overall, the actual data. This is also because in the data sets that we download from the internet, the simulation results are available. We wanted to compare against everything, just to make sure that what we're doing was, in fact, worthwhile. And what you see is that the 7 numbers here represent the different, or the 7 joints of the arm. And what can be seen is that our method, in fact, performs quite well. And so the error is pretty much, the accuracy and the overall mean square error of the approximation is fairly good. And these are results, by the way, not on the data set we use for training. These are test data, which means the 5,000 samples that weren't used for training. So there's a sort of cross-check that what we're doing actually works for data that were never seen by the training procedure. So that's completely new data on the same robots, of course, but new data points. And from the plots, for instance, it's easy to visually compare the different bars and see that our method does pretty well and does a good job in doing this approximation, compares favorably against other methods. And this other slide shows the same thing for the other robot, the Barrett robot, so the second one. And again, performance is quite good. The quality of the approximation varies a bit depending on the number of points we used in the approximation. The nice thing, though, is to compare against prediction time. Prediction time, by the way, is the time it takes to compute a solution once you learned it. So as you can see, there's one important thing. In this plot, we plot against training sample. Basically, all methods start with a reasonable, let's say, computation time, but then the cost of the solution grows with basically the square or the cube of the number of training points, which is clearly not feasible because as you keep adding training points, the solution becomes easily too expensive to compute. While for our method, it remains constant, which is basically what we wanted to obtain. We knew in advance that it remains constant. So for instance, computational dynamics, when we use 500 points in the approximation of the kernel, turns out to be below 0.1 milliseconds, which is super good because it's super efficient. If you increase the approximation quality a bit, you're still below 0.2 milliseconds. So in all our tests, we compute a solution very efficiently. Imagine a control loop for the robot movement that includes the dynamics. Everything has to be computed in less than 1 millisecond typically. And in this case, adding the dynamics computation takes only 0.2 milliseconds additionally. So which is important, is good. And there's irrespective of the number of data points. So we can keep adding points and the solution will still be computed in the same amount of time. Then we ran through, these were batch experiments. So we taken the entire data set and we trained the method and then we tested it separately. Then we ran actual incremental experiments, simulating the fact that the robot is collecting data as it moves, and you want to have a new solution at each instant of time, updating the solution as you collect more data. We did it again for the Sarcos robot, which is the hydraulic robot, and we did it for 2 more robots, for 2 more different robot arms that we had available in our lab. And in this case, we also collected 5,000 samples and another number of, let's say, samples to actually do the test. And these are the results compared against other methods, again, for the, let's say, the various robots. And as it can be seen, this newly developed method approximates the solution quite well. It's in fact, if you look at the numbers, a lot better than existing methods. And it compares also favorably with a non-approximate method, which is shown here, mentioned as GPR, which is basically very similar to ours, but doesn't approximate the kernel, which means the computation time will increase over time. So of course, these are experiments we've done in a computer, so we don't care. But to the actual usage of the method in the robot, it's important that the time of computation remains constant. And there's another thing that is nicely done with this ability to manipulate the kernel. So we know the method works. There's another thing that is important. So the Forster sensors are based on semiconductor strain gauges, which are these little devices that measure the strains in a mechanical component. So as the robot moves, these deformations are measured. There's one problem with semiconductors. It's not very much the environment temperature that is important, but the fact that the robot is full of electronics. Maybe the sensors are nearby the motors, and the motors generate heat. And so it's very likely that local temperature changes quite a lot, and so the sensor starts drifting. There's one way to use machine learning to compensate for that, and that turns out to be, let's say, related to the fact that we can play with the kernel. So we can have a kernel that is augmented. It includes all the random features from the Fourier decomposition that we mentioned earlier, plus a term that just depends on time. And this is basically a way to take exactly the same method and with a minor modification take into account of the fact that there may be a temperature drifting. And what happens is that also incrementally, the solution will add a linear term function of time, so a trend, and compensate automatically for that. And that's what we've done. And the results in these plots show basically results on the ICAB showing that we can actually compensate for temperature variations. There's a comparison. The blue lines are without compensation. The red lines are with compensation. And those are with compensation are a lot flatter, which means the temperature drifts are actually being removed. So in summary, what we've done allows a fast prediction. I have a few numbers here, like for 1,000 random feature approximation, it takes, let's say, 7 milliseconds. And for the 200 random feature approximation, it takes 400 microseconds. So that's just to give an idea. And that's probably can be optimized further. I mean, if it had to be actually inserted, can be probably computed in hardware, or it's a solution that is simple enough to be computed in specialized microcontrollers, so DSPs that can do an even more efficient job. And then also the fact that we can compensate for temperature is a positive fact. And then one thing that we noticed is, in fact, that if you use more than 1,000 random feature, there's no gain in the actual approximation quality, which means that this is a case. I mentioned earlier that the fact that dynamics is a simple problem in a sense. And so for this specific task, is more than 1,000 is not actually required, which is super good because you know, okay, I'll do 1,000, that's it. I don't have I forget about the fact that I have to tune dynamically the resolution of the method, which is again an interesting concept. Now, since we had the method, we decided to attack another problem, which is very basic in robotics, that has to do with point-to-point movements. So if you have to move the arm from one point to another across using, for instance, a linear trajectory, you have to compute the inverse kinematics, which means determining the movement of the joints in order to obtain a movement of the hand that is along a straight path. We've done this using, again, a method that has been developed by us, and it basically uses two components. The first component is a nonlinear optimization method. This is, again, let's say, relatively recent mathematics. It's an optimization method that finds a solution taking into account also constraints. So it's a constrained nonlinear optimization, which is good because a robot that moves has a lot of constraints. Joint limits are one. You may want to impose, I don't know, other constraints on the orientation of the hand rather than the height of the elbow while you move. And these are all controllable using this type of methods. So what we do, we use the nonlinear optimizer to find the inverse kinematic solution, taking into account of the constraints. And then what we have is a trajectory generation method that takes into account both the movement of the joints and the movement of the hand, and simultaneously tries to go along a straight line. But if it sees that reaches a kinematic singularity, so a configuration that the robot cannot really achieve, it drifts a bit from the straight line, adjusting with small adjustment of the joints, so to be able to actually make the movement. I mean, if you reach a singularity, you cannot move, so that has to be taken into account. What we show, for instance, in these plots are the fact that the target is reached in the case of even a complicated, let's say, trajectory that has to go around an object and reach from a bit from behind the object. The solution, which is showing green here, is very robust. I mean, is almost a straight path, and with a curvature that depends on the fact that you have to orient your hand with respect to the object, but compares favorably against other methods that are shown here, which either oscillate too much. The red line is a method that is, let's say, a very well-known method in robotics, which is the Jacobian pseudo-inverse. It's fairly well known. And the other method is another possible solution that is kind of inspired from the control of human muscles. But in this case, as the problem that has too much variability. So depending on the initial conditions, the solution changes quite a lot, and that's not good. So for repeated trials, you actually use different trajectories. So while on the other hand, you will expect always to go along the same trajectory if the object is roughly in the same position. And this is shown here. The shaded areas in the plot are actually the error bars along the plot over a number of repetitions. The other thing we've done was to generate trajectories that are as much as possible human-like. And so we can actually impose the fact that the trajectory velocity has a certain profile. So it starts slow, is increased, and then slows down to reach the object. That's, again, I think it's a nice way of controlling a robot in such a way that is good for human-robot interaction. A robot that pretty much moves like a person. So this is, the next slide is about the mathematics behind it. So there's it's shown what specific function we optimize for doing this implementation. And the nice thing about this is that we can basically impose the fact that the hand reaches the target point with a certain orientation. We can impose the height of the elbow, so whether you go with a trajectory that goes, flat with respect to the height of the robot and target, or rather goes up a bit and then goes down later. And then as constraints, we can impose the joint limits and also the fact that the hand has to reach as much as possible the object for maybe grasping later. And the slide shows also, basically the solution and the trajectory that is actually generated, taking into account all these constraints and the kinematic singularities that I mentioned earlier. So it all works well. The entire method depends on knowledge of the kinematics of the arm. The kinematics of the arm can also be learned, in fact, from data. Because we can take data points and do the learning. What is shown in the next slide is how we get the data points, and it's basically by using vision. So we have cameras that can identify the position of the hand and the position of the target. And so what we can do is take the position of the hand, and as the hand moves in the cameras, we know the 3D position of the hand. At the same time, we know the joint angles. And a mapping between the joint angles and the 3D position of the hand is, in fact, the direct kinematics of the robot. So we collect the data, and we also use the same learning method we used before, because we have points in this space. We want to approximate a function that maps joint angles, in this case, to the 3D position of the hand. This plot, the next plot, shows the type of data we have to deal with, noisy in a sense, and we show later how it works once we do learning. Also in this case, we've done a comparison with other methods. There's a plethora of possibilities for learning kinematics, and what is shown here is, in fact, that again, our implementation works particularly well, and as we increase the number of, let's say, points in the approximation of the kernel, we increase performance, and up to a certain point. Again, the limit is kind of 1,000 points in the approximation to do a good job. And this is with constant computational time, which is again, as before for the dynamics. So also in this case, we can do a nice thing, and we've been able to actually learn the kinematics of the robot pretty efficiently. Okay, I think I'm done with this part of the presentation. I think the nice thing is that it introduces machine learning to two robotics related problems. One is dynamics, the other one is kinematics. Those are the basics again for control, and we've shown that both of them can actually be learned. So you don't need to specify these things on a new robot. You can actually use your sensors to learn them. And that's what we like to obtain. At the end of the day, we want to have software methods that you plug into a robot, however the structure of the robot is, and you learn both the structure and the controllers autonomously. The robot will follow calibration phase to collect the data, and then will move nicely because it learned how to move. And next, let's say, continuing from this, the same methods can be applied to more complicated tasks, where it's more the artificial intelligence that plays a role, while here we're still at the level of building controllers.